right, we are ready to finish up the very last lecture of Unit 4. Hopefully those balancing problems went very well for you. They are challenging and they do involve several steps, but you had 6 of them to do. And one of those 6 problems is going to be on the test tomorrow or Thursday when you take your test. We'll cover the review very thoroughly with you over the Google Meet. Okay, so this was the last problem we finished off with. It was kind of a unique case of hydrogen peroxide, sort of both being oxidized and reduced the oxygen. This is the oxidation half reaction. As you can see here, we finished that up last time, and then I said we would start today with a basic solution and see what the difference is there. Okay, so the good news on this is when you're doing a basic solution is you aren't going to have to reinvent the wheel here. The problems start out pretty much the same. There are a few changes. For instance, permanganate, if you're using permanganate, it does not turn into Mn+2, but it'll actually convert over to MnO2. So it goes from a +7 to a +4. So that is a reduction in oxidation numbers. So it's a reduction reaction. But that was different than it was with oxidation, where it went from +7 down to +2. So it just goes to a different form if it's in a basic solution. So that means when we have the potassium permanganate, again, the business part is the permanganate, and then sodium out of play, always those family 1, don't worry about them, and then sulfite. You remember we can talk about the oxidation of that sulfur. So here is the overall equation. The sulfite becomes sulfate. So that is the same. Now we need to use balance this using our special and quite intense method, because virtually impossible to balance as is, and you won't get the right answer even if you could figure it out by trial and error. So we are going to start with the reduction half reaction, and as we mentioned, since the manganese goes from +7 down to +4, that is a reduction, so that's our reduction reaction. You can see step 2, the Mn, they're the same. You don't have to worry about that. Step 3, however, we are going to have to fix the oxygens by adding 2 water molecules to the right side. As you can see, I'm going to go through this a little faster, so don't hesitate to hit the pause if we're going too quickly here. And right at this point, you've got the 4 hydrogens over there to compensate for the water that you added to the right side. So now you can look at this reaction. It is a reduction, so that means the electrons have to go on the reactant side. So I need to add enough electrons to get rid of the excess plus charges. Now there's no charges on the right side, but you do have 4 pluses, and then with that minus, that makes 3 pluses. So you're going to have to add 3 electrons to get rid of the 3 positive charges on the left side. So hopefully something like that, you look at that and you go, yeah, I got that. And the only thing that really changed was the permanganate undergoes a different process. All right. This reaction would be the same whether it's acidic or basic. For oxidation, sulfurs are balanced. Oxygens you are going to have to fix by just adding 1 water, and then compensate on the other side by adding 2 hydrogens. This one's a little bit trickier with the charge. You know the electrons have to end up over here, but you can see the 2 minuses cancel each other out, so you can really just leave that out of the mix and go, hey, I just need to add 2 electrons there to get rid of the 2 pluses from the excess hydrogens right there. So that's a 2E minus. It's right, my little pictures kind of overlapping that right there. So so that works out really nicely, and you have now done steps 1 through 5 for each of them, and you need to do the old crisscross method. If you have 3 electrons and 2 electrons, you're going to have to multiply this whole thing by 2 and that whole thing by 3, and those are your actual correct half reactions on step 6. Step 7 is to stack them and cross them out, and you can see the electrons will cancel out, and your overall reaction is this right here, except this ain't gonna cut it. And the reason is because, so up to this point, it's basically the same thinking process with acidic or basic, like I said, with that one exception with the permanganate. But at this point, you can't really have an excess of H pluses if it's a basic solution. So we need to get rid of that. You still use them to balance the equation, but there is a way, because it's a basic solution, there is a step 8. So, and you're going to be doing just one step 8. So you're not going to have to do the whole problem. Remember, there are 6 of these problems. You're doing one of those 6, and then on the test there will be one where I give you this and I say, okay, show me step 8 in this basic solution. So what you do in a step 8 is you add just enough OHs to get rid of the hydrogen on this side. Now notice it's not going to just completely disappear, and this is where it gets a little bit tricky, because the OH and the H plus, if you think about that, makes a lot of sense. Those charges are going to go, and you got H2O. So we have 2 water molecules, but we have 1 water molecule on that side. Okay, so 2 water molecules as a reactant, 1 as a product, and then that leaves with a net, because you just like subtract 1 water molecule from each side, you end up with a net of 1 water molecule on that side, and of course the 2 OHs are still over there on that side. So that's all you got to do. There are practice problems for you to look at. You don't have to submit these, but you can look at I think 3 examples in basic solutions where you add that hydroxide ion at the end. You get some water that you'll have to cancel out, and you'll have 2 OHs or OHs left over because it is a basic solution. All right, you'll add to one side to get rid of the hydrogen ions, and then the other side will leave an excess of OH. All right, so that's the extra step that you add. All right, and this last thing is just a little, we're just going to dabble a little bit into redox titrations. This is definitely something we'll be doing more as a lab, but what you're going to do is you're going to set up a reaction where there's a nice color change like this. Permanganate is a perfect example, and I'm hoping that we'll work in a lab where we actually do this. So you can put in a known concentration of permanganate ion, that being purple. And then you can put this iron +2 solution. And as long as there's sufficient iron +2 ions available, what will happen is that will change, in this case reduce, the purple permanganate into a colorless solution. And it'll do that, and it'll do that, and it'll do that. You add a drop, colorless, drop, colorless, drop, colorless. And then there'll be a magic drop that you put down where there is no longer any enough of this MnO4 runs out, and then so that it won't react. This iron +2 ion right here will run out, and then the excess MnO4 will just turn the water kind of pinkish purpley color. All right, and it won't. It'll stop reacting. So the excess will just stay in solution, and you'll have MnO4 will stay in there instead of reacting and becoming colorless. So what happens is you can run out of one of these. So this is the key, is this +2. We don't know what the concentration of that is, but we know it's like in a 5-to-1 ratio, molar wise. We do know the exact concentration of the KMnO4. That's very easy for me to figure out, and I'll weigh that out for you. So we'll just read through this problem, and then you can read through the example problems. And like I said, this is more of a kind of a lab type of activity where you actually get to see this happening. So step 1 says find the moles of KMnO4 delivered in this particular problem. You simply take the milliliters, convert that to liters, liters to moles using the known concentration. Remember that concentration was known. So then we have put that many moles in. And then to find the moles in the analyte, which is the stuff in the bottom there, you go, hey, this is a 1-to-5 molar ratio. That's a mole-to-mole conversion using the coefficients in the balanced chemical equation. So you got the MnO4 in a 1-to-5 ratio. That's how many moles of Fe+2 you have. And then that didn't answer the concentration. So then you just say, well, there was 0.300 liters of it. There's that many moles. Concentration is moles per liter, and you do your final concentration. Okay, so that's the last kind of problem in this unit, so good luck on your exam, either tomorrow or on Thursday, depending on when you're going to be in school. And if you're not going to be in school, then it will be on Thursday. All right, so end of Unit 4.